What if I told you that right now, somewhere in the fabric of the universe, there might be a tunnel, a shortcut, a bridge that could take you from this planet to a galaxy 2.5 million light years away in less than a single heartbeat? What if I told you that the mathematics of our universe, the very same equations that predict the orbits of planets, the bending of light around stars, the expansion of the cosmos itself, those same equations allow for the existence of something so extraordinary, so mind-bending, that even the man who discovered them refused to believe they could be real? And what if I told you that this same tunnel, this same cosmic shortcut, is also the single most dangerous structure that could theoretically exist in all of physics? A structure so violent, so unstable, so fundamentally hostile to anything that dares to enter it, that it would tear you apart atom by atom, crush you into oblivion, and erase every trace of your existence before you could even blink. Welcome to the world of wormholes, the universe's deadliest shortcut. Now, before we go any further, I want you to just pause for a second and think about this. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means if you were traveling at the speed of light, the fastest speed anything in the universe can travel, it would still take you over 4 years to get there. 4 years traveling at 300,000 kilometers per second. And that is just the nearest star. The nearest large galaxy to us, the Andromeda Galaxy, is 2.5 million light-years away. 2.5 million years at the speed of light. The observable universe stretches 93 billion light-years across. These distances are not just large, they are prison walls. They are the bars of a cosmic cage that traps every civilization, every species, every conscious being on whatever tiny rock they happen to be born on. The speed of light is not just a speed limit, it is a life sentence. And there is no parole. Unless, of course, there is a shortcut. And here is where things get absolutely wild. Because in 1935, one of the greatest minds in human history, Albert Einstein, working with his colleague Nathan Rosen at the Institute for Advanced Study in Princeton, New Jersey, published a paper that would accidentally reveal one of the strangest possibilities in all of physics. They were not looking for tunnels through space. They were not trying to invent faster-than-light travel. They were trying to solve a completely different problem. They were trying to understand particles. Specifically, they were bothered by singularities, those points in the equations where numbers blow up to infinity, where the math breaks down, where physics essentially throws its hands up and says, "I do not know what happens here." Einstein hated singularities. He believed that a proper theory of the universe should not have infinities in it. So he and Rosen sat down and tried to rewrite the equations of general relativity in a way that would eliminate these troublesome points. And what they found shocked them. When they reformulated the Schwarzschild solution, which describes the geometry of spacetime around a spherical mass like a black hole, they discovered that the mathematics naturally produced something extraordinary. Two complete separate copies of spacetime, two entire universes, if you will, connected by a narrow bridge. A bridge at the point where the singularity used to be. They called it simply a bridge. The Einstein-Rosen bridge. And this was the first time in the history of physics that the equations of our universe had formally predicted something like a tunnel connecting two different regions of reality. But here is the thing that most people do not know. Einstein himself did not think you could travel through it. He saw the bridge as a mathematical trick, a clever way to get rid of singularities, not as a literal portal. In his mind, it was a theoretical curiosity, nothing more. He had no idea that this accidental discovery would eventually inspire decades of research, spark entire fields of theoretical physics, influence countless works of science fiction, and lead us to some of the deepest questions about the nature of reality itself. Now, if you are someone who is curious about the universe, if you are someone who lies awake at night, wondering what lies beyond the edges of what we can see, if you are the kind of person who wants to understand not just what the universe is, but what it could be, then I need you to stay with me for this entire journey. Because what we are about to explore together is not just a story about tunnels through space. It is a story about the very nature of space-time itself, about the deepest connections between gravity and quantum mechanics, about time and whether it flows in one direction or two, about parallel universes and whether they might be connected to ours, and about the bleeding edge of research happening right now in 2026 that is fundamentally changing everything we thought we knew about these mysterious structures. So settle in, get comfortable, because this is going to be a deep, thorough, and I hope truly mind-expanding conversation. Let us start from the very beginning. To understand wormholes, you first need to understand the stage on which they exist, and that stage is space-time. In 1905, Albert Einstein published his special theory of relativity, which, among many other revolutionary ideas, showed that space and time are not separate things. They are woven together into a single four-dimensional fabric called spacetime. You exist in 3 dimensions of space, length, width, and height, and 1 dimension of time. These 4 dimensions together form the arena in which all of physics takes place. Everything that happens, every event, every movement, every interaction occurs within this 4-dimensional fabric. Then, in 1915, Einstein went further, much further. He published his general theory of relativity, which revealed something astonishing about this fabric. It is not rigid, it is not fixed. It can bend, it can stretch, it can warp, and what causes it to bend is mass and energy. When you place a massive object like a star or a planet in space-time, it curves the fabric around it. And this curvature is what we experience as gravity. The Earth does not orbit the Sun because some invisible force is pulling it. The Earth orbits the Sun because the Sun's enormous mass has curved space-time around it, and the Earth is simply following the most natural path through that curved geometry. Gravity is not a force in the traditional sense. It is the geometry of space-time itself. Now, here is the analogy that most people use, and it is a good one to start with, even though it is not perfect. Imagine a large rubber sheet stretched out flat. This represents space-time, though we are reducing it from 4 dimensions to 2 for visualization. Now, place a heavy bowling ball in the center of the sheet. The sheet sags, creating a curved dip around the bowling ball. If you now roll a marble across the sheet, it will not travel in a straight line. It will curve around the bowling ball, following the contour of the depressed rubber. That curving path is what we call an orbit, and the depression in the sheet is what we call gravity. This is, in a very simplified way, what Einstein's general relativity tells us about the universe. But this analogy also gives us the intuition for wormholes. Imagine that rubber sheet again. Put 2 points on it, very far apart. Call them point A and point B. An ant walking along the surface of the sheet would have to travel the entire distance between them, following the flat surface. That is conventional space travel. Slow, limited by the speed of light, constrained by the vast distances of the cosmos. But now imagine folding the sheet so that point A and point B are directly on top of each other, with only a small gap between them. Now poke a hole through the sheet connecting the 2 points. The ant can crawl through that short tunnel and get from A to B almost instantly, even though they are enormously far apart along the surface. That tunnel through the folded fabric is a wormhole. But I need to be very clear about something important here, because this is where many popular explanations go wrong. In reality, space-time is not being literally folded like a piece of paper. What is actually happening is far more subtle and mathematically precise. The equations of general relativity allow for space-time geometries in which 2 distant regions are connected by a throat, a narrow passage through higher dimensional geometry. The embedding diagram, that famous image of 2 funnel shapes connected at their narrow ends, is a 2-dimensional representation of a higher dimensional reality. We lose information in the visualization. The actual physics is described by a metric, a mathematical object that tells you the distances between points in space-time. And certain metrics, certain solutions to Einstein's field equations, naturally produce these bridge-like connections. So what does a wormhole actually look like? If you could somehow travel to a wormhole and look at it from the outside, you would not see a flat circle, a spinning vortex, or a glowing portal like in the movies. You would see a sphere, a 3-dimensional sphere floating in space. And through that sphere, you would see a distorted, lensed view of whatever is on the other side. If the other end of the wormhole opened up near a distant galaxy, you would see that galaxy stars, nebulae and planets, through the spherical mouth, distorted and bent by the extreme gravitational lensing around the wormhole's throat. It would look like a crystal ball showing you another part of the universe. This is actually what the movie Interstellar got beautifully right, thanks to the involvement of Nobel Prize-winning physicist Kip Thorne, who served as the film's scientific advisor and whose work on wormhole physics is among the most important in history. Now, let me introduce you to a critical distinction that changes everything about how we think about wormholes. Because not all wormholes are created equal. And the difference between the types is quite literally the difference between life and death. The first type is what we call a Schwarzschild wormhole, or the original Einstein-Rosen bridge. This is the kind that naturally appears in the mathematics of an eternal, non-rotating, uncharged black hole. And this type of wormhole has a fatal problem. It is non-traversable. In 1962, two physicists, John Archibald Wheeler, the same man who coined the term wormhole, and Robert Fuller published a devastating paper proving that Schwarzschild wormholes are catastrophically unstable. They showed that the bridge pinches off, collapses shut, faster than the speed of light. This means that even if you are traveling at the maximum speed the universe allows, you could not get through before the throat closes and crushes everything inside it into a singularity. Nothing can cross a Schwarzschild wormhole. Not matter, not light, not information, nothing. It exists for a fleeting moment in the mathematics, a ghostly bridge that appears and vanishes before anything can use it. It is the ultimate tease, a door that opens and slams shut before you can take a single step through it. And this discovery, this proof by Wheeler and Fuller in 1962, essentially killed wormhole physics for over 2 decades. After their paper, most physicists simply lost interest. Wormholes became a purely academic curiosity, a mathematical artifact with no physical relevance. They were interesting on paper, useless in reality. The field entered what you might call a dark age, with almost no serious research being done on traversable wormholes. And then something remarkable happened, something that shows how the most important breakthroughs in science can come from the most unexpected places. In 1985, the famous astronomer and science communicator Carl Sagan was writing a novel called Contact. You might know it from the 1997 movie starring Jodie Foster. In the story, Sagan needed a scientifically plausible way for his main character, Ellie Arroway, to travel across the galaxy to meet an alien intelligence. He did not want to use something completely made up. He wanted something grounded in real physics. So he picked up the phone and called his friend Kip Thorne at the California Institute of Technology. Thorne was one of the world's leading experts in general relativity. Sagan asked him a simple question. Is there any way within the known laws of physics to travel faster than light or cross vast distances quickly? And Kip Thorne's answer changed the history of physics. Thorne thought about it carefully and told Sagan to use a wormhole, but not a Schwarzschild wormhole, the unstable kind that Wheeler and Fuller had killed. A different kind. A traversable wormhole, one that could be held open by something called exotic matter. This conversation, a phone call between a science fiction writer and a theoretical physicist, reignited an entire field of research. Thorne became fascinated by his own suggestion. He went back to the equations and, working with his graduate student Michael Morris, produced a landmark paper in 1988 titled Wormholes in Spacetime and Their Use for Interstellar Travel, published in the American Journal of Physics. This paper was revolutionary. Morris and Thorne did not just speculate about traversable wormholes. They wrote down the exact mathematical requirements. They derived a specific metric, now known as the Morris-Thorne metric, that describes a wormhole you could actually travel through, and they listed the conditions that such a wormhole would need to satisfy. It must not have an event horizon, otherwise you could enter but never leave. The tidal gravitational forces at the throat must be small enough that a human could survive the passage, no more than about 1 g of tidal acceleration. The travel time through the wormhole must be reasonable, not millions of years. And the wormhole must be stable, it must not collapse when something enters it. These were the engineering specifications for a traversable wormhole, a blueprint, if you will, for the universe's ultimate shortcut. But the blueprint came with a price tag, and that price tag was exotic matter. To understand why exotic matter is necessary, you need to understand something about how gravity normally works. Normal matter, the stuff you and I and stars and planets are made of, has positive energy density. It curves space-time inward. It attracts. Gravity pulls things together. This is why the throat of a Schwarzschild wormhole collapses. The gravity of the wormhole itself pulls the walls inward, squeezing the throat shut. To keep a wormhole open, you need something that does the opposite. You need something that pushes space-time outward, something with negative energy density. Something that has repulsive gravity instead of attractive gravity. This is what physicists call exotic matter. Now let me be very precise here because this is an area where there is a lot of confusion. Exotic matter is not the same as antimatter. Antimatter is real. We produce it in particle accelerators every day, and it has positive mass and positive energy just like normal matter. An anti-electron, or positron, has the same mass as an electron, just opposite electric charge. If you dropped a ball of antimatter, it would fall down, not up. Antimatter gravitates normally. Exotic matter is also not the same as dark matter. Dark matter, whatever it turns out to be, also has positive mass. It gravitates normally, which is exactly how we detected its existence in the first place, by observing its gravitational effects on galaxies and galaxy clusters. And exotic matter is not quite the same as dark energy either, though dark energy does have some interesting properties involving negative pressure that are worth discussing. Exotic matter, in the context of wormhole physics, is matter with genuinely negative energy density. And the crucial question is, can such a thing exist? Can you have a region of space where the energy is less than zero? And the answer, remarkably, is yes. We know this because of the Casimir effect. The Casimir effect is one of the most beautiful and surprising results in quantum physics. It was predicted by the Dutch physicist Hendrik Casimir in 1948 and has been experimentally confirmed multiple times since then. Here is how it works. Take two perfectly flat, uncharged metal plates and place them extremely close together in a vacuum. We are talking distances on the order of micrometers. Now, in quantum field theory, even empty space, a perfect vacuum is not truly empty. It is seething with quantum fluctuations. Virtual particles are constantly popping into existence and annihilating. These fluctuations exist everywhere, both between the plates and outside the plates. But here is the key. Between the plates, only certain wavelengths of these fluctuations can fit. The plates act as boundaries that restrict which fluctuations can exist in the gap. Outside the plates, all wavelengths are allowed. This means there are fewer quantum fluctuations between the plates than outside them. The result is a net pressure pushing the plates together from the outside. This is the Casimir force, and it has been measured in the laboratory with high precision. But here is the part that matters for wormholes. The energy density between the plates is lower than the energy density of the vacuum outside. Since we normally define the vacuum energy as zero, this means the region between the plates has negative energy density. It is below zero. The Casimir effect proves that negative energy density is not just a theoretical fantasy. It is a real, measurable phenomenon that exists in our universe. However, and this is a very big however, the amount of negative energy produced by the Casimir effect is incredibly, unimaginably tiny. We are talking about energy so small that they are barely detectable with our most sensitive instruments. To hold open a wormhole large enough for a person to travel through, early calculations by Morris-Thorne suggested you would need roughly the mass energy equivalent of the planet Jupiter, but in negative energy, compressed to the size of the wormhole's throat. Later refinements by physicists like Matt Visser showed that the amount could in principle be made much smaller, perhaps even arbitrarily small. But arbitrarily small, in the language of theoretical physics, still means enormously beyond anything humanity can currently produce or even conceive of producing. We cannot take the Casimir effect and simply scale it up by a factor of 10 to the power of 40 to create a wormhole. The gap between what we can do and what we would need to do is not a gap. It is an abyss. But here is where things get really interesting and where the research has been evolving rapidly, because it turns out that exotic matter might not be the only way to keep a wormhole open. In 1989, just a year after Morris-Thorne's landmark paper, Matt Visser at Victoria University of Wellington in New Zealand proposed a different approach. He developed what is now called the thin shell wormhole, sometimes also known as a Visser wormhole. His construction uses the cut-and-paste technique, which is exactly what it sounds like. You take two copies of a space-time solution, like two Schwarzschild black holes, cut out the problematic regions containing the singularities, and glue the remaining pieces together at a thin shell. The exotic matter is confined to this thin shell, and here is the beautiful part. The path that a traveler takes through the wormhole does not actually pass through the region containing exotic matter. You travel through the wormhole without ever touching the exotic stuff. This dramatically reduces the amount of exotic matter needed, and also avoids some of the theoretical problems associated with having matter pass through negative energy regions. But the innovations did not stop there. In some modifications to general relativity, wormholes do not need exotic matter at all. In what is called Gauss-Bonnet gravity, which arises naturally in certain versions of string theory and involves extra spatial dimensions beyond the three we experience, wormholes can exist with no matter whatsoever. They are purely gravitational structures, supported entirely by the modified geometry of spacetime in higher dimensions. In a framework called F-gravity, where the gravitational action is modified from its standard form, wormhole solutions also exist without requiring violations of the classical energy conditions. And in January 2024, a particularly exciting paper was published showing that in the Randall-Sundrum-Branwell model, which is a scenario from string theory where our universe is a membrane floating in a higher dimensional space, traversable wormholes could potentially be stabilized by ordinary electrically charged fermionic matter, no exotic matter with electric charge, and small enough mass that it cannot collapse into a charged black hole. If this model is correct, and that is a significant if, then microscopic traversable wormholes might be far more achievable than we ever imagined. Now, I want to take a moment here to address something important. Throughout this discussion, I have been careful to use words like theoretical, hypothetical, and if. And that is because, as of right now, in 2026, we have zero observational evidence that macroscopic wormholes exist anywhere in the universe. None. Not a single confirmed detection. Everything we have discussed so far is based on mathematics. The equations of general relativity permit wormholes, just as they permit black holes. But we have directly detected black holes. We have seen their shadows with the Event Horizon Telescope. We have heard them collide through gravitational wave detectors. We have overwhelming observational evidence that black holes are real physical objects. For wormholes, we have nothing comparable. They remain, for now, theoretical constructs. Beautiful, mathematically consistent, deeply fascinating theoretical constructs, but theoretical constructs nonetheless. That said, the absence of evidence is not evidence of absence, and there are serious credible scientists working right now on methods to detect wormholes if they exist. So, let me walk you through how we might find one. The first method involves gravitational lensing. As we discussed, gravity bends space-time, and anything that bends space-time also bends the path of light. A massive object like a star or a black hole acts as a gravitational lens, distorting and magnifying the images of objects behind it. A wormhole would also act as a gravitational lens, but with a crucial difference. A black hole creates a characteristic pattern of lensing, an Einstein ring, that depends only on the mass and the alignment of the observer, lens, and source. A wormhole, however, has a throat. Light from the other side of the wormhole could pass through the throat and emerge from the mouth on our side. This means that in addition to the lensing effects you would expect from a massive object, a wormhole might also show you a direct image of whatever is on the other end. If the other end opens up near a completely different part of the universe with different stars and a different night sky, you might literally see that alien sky superimposed on our own. The gravitational lensing signature of a wormhole would be subtly but measurably different from that of a black hole, and several research papers, including detailed calculations by physicists like Rajibul Shaikh and others, have worked out exactly what these differences would look like. The second method involves gravitational wave echoes. When two black holes merge, they produce gravitational waves that we can detect with instruments like LIGO and Virgo. The gravitational wave signal from a merger has a characteristic shape, a chirp that increases in frequency and amplitude, followed by a ring down as the merged object settles into its final state. But if the resulting object is not a black hole but a wormhole, or if the merging objects were wormholes rather than black holes, the signal would be different. Specifically, gravitational waves could bounce back and forth inside the wormhole's throat, producing echoes in the signal. These echoes would appear as repeated, diminishing pulses after the main merger signal. Several groups have searched the LIGO data for such echoes, and while no confirmed detection has been made, the search is ongoing and the methods are becoming more sophisticated. The third method involves the shadow of a wormhole, the Event Horizon Telescope, which famously captured the first image of a black hole shadow in M87 in 2019, could potentially distinguish between a black hole and a wormhole. The shadow of a black hole, the dark silhouette created because light that falls past the event horizon never comes back out, has a very specific shape and size predicted by general relativity. A wormhole would not have a true event horizon, if it is traversable, and light from the other side could pass through the throat. This means the shadow of a wormhole might look different, perhaps smaller, perhaps with a different edge profile, perhaps with light from the other end visible in the center of the shadow. Detailed calculations have been done for various wormhole models, and the differences, while small, are in principle detectable with future generations of very long baseline interferometry. And then there is the fourth method, which I find the most tantalizing and the most controversial. It involves a specific gravitational wave signal that was actually detected. This is the story of GW190521. On May 21, 2019, the LIGO and Virgo gravitational wave detectors picked up a signal. Analysis indicated that it came from the merger of two truly massive black holes, approximately 85 and 66 solar masses, respectively, creating a final black hole of about 142 solar masses. Now, this was already an exciting detection because it provided the first evidence for intermediate mass black holes, a class that had been theorized but never confirmed. But there was something strange about it. The masses of the two merging black holes fell within what is called the pair instability mass gap. According to our understanding of stellar evolution, stars in a certain mass range undergo a process called pair instability supernova when they die. The intense gamma radiation in the star's core creates electron-positron pairs, which reduces the radiation pressure holding the star up, causing it to contract and then violently explode. This process should completely destroy the star, leaving nothing behind, no remnant. No black hole. It means that black holes in the mass range of roughly 65 to 120 solar masses should not be able to form from the collapse of a single star. They should not exist. And yet GW190521 seem to involve black holes right in this forbidden range. So where did they come from? One explanation is that they formed from the merger of smaller black holes in dense environments, like globular clusters. That is the conventional explanation, and it is perfectly plausible. But a team of researchers proposed a much more exotic possibility. What if the signal did not come from our universe at all? What if two black holes merged in another universe entirely, and the gravitational wave signal from that merger traveled through a wormhole connecting that universe to ours and was picked up by our detectors? The team developed a specific mathematical model, a wormhole waveform template, describing what a gravitational wave signal would look like if it passed through a wormhole throat. They compared this template to the GW190521 data, and they found that the fit was surprisingly good. Now, I want to be extremely clear about this. This is a highly speculative hypothesis. The vast majority of physicists accept the conventional explanation for GW190521. The wormhole interpretation is a minority view and has not been confirmed by any independent analysis. But it is a legitimate scientific hypothesis that has been published in peer-reviewed journals and is being actively discussed in the gravitational wave community. It is the kind of idea that keeps physics exciting, the possibility that we might have already inadvertently detected evidence of another universe. Now let us return to the question that probably brought many of you here in the first place. What would actually happen if you tried to travel through a wormhole? And this is where the deadliest shortcut part of our title really comes into focus. Let us consider each of the ways a wormhole could kill you. And there are many. The first and most immediate danger is gravitational tidal forces. As you approach the throat of a wormhole, the gravitational field becomes enormously strong and enormously uneven. Your feet, being closer to the center of the throat, would experience significantly stronger gravitational pull than your head. This difference in gravitational force across the length of your body is called a tidal force. And in the vicinity of a wormhole throat, especially one with a small radius, this tidal force becomes extreme. Your body would be stretched in the direction toward the center and compressed from the sides, like being put on a cosmic torture rack while simultaneously being squeezed in a vice. Physicists have a wonderfully evocative term for this process. They call it spaghettification. Your body would be drawn out into a long, thin strand like a piece of spaghetti before being torn apart at the molecular and then atomic level. Morris and Thorne specifically addressed this in their 1988 paper, stating that for a wormhole to be safely traversable by humans, the tidal acceleration experienced by the traveler must not exceed roughly 1 Earth gravity. This places strict constraints on the size and geometry of the wormhole, essentially requiring the throat radius to be quite large, which in turn increases the amount of exotic matter needed. The second danger is radiation. Even if the tidal forces were somehow manageable, the space near a wormhole throat would be flooded with radiation. Any photons, any electromagnetic radiation that happens to be in the vicinity would be gravitationally blue-shifted as it falls toward the throat. This means that ordinary harmless background radiation, the cosmic microwave background for instance, would be compressed to higher and higher frequencies as it approaches the throat. Infrared light would become visible light. Visible light would become ultraviolet. Ultraviolet would become X-rays. X-rays would become gamma rays. By the time you reached the throat, you would be immersed in a bath of lethal high-energy radiation. And this is just the ambient background radiation. If there is any matter, any gas, any dust near the wormhole, its thermal radiation would also be blue-shifted to dangerous levels. You would essentially be cooked alive by the accumulated radiation at the throat. The third danger is the instability of the wormhole itself. Even if we assume that exotic matter or some modified gravity effect is holding the wormhole open, the stability of that configuration is extremely precarious. The wormhole throat is like a house of cards. Any perturbation, any disturbance could trigger a catastrophic collapse. And here is the deeply ironic part. The very act of trying to travel through a wormhole could be the thing that destroys it. When you enter the wormhole, you introduce additional mass and energy into the throat region. This changes the curvature of space-time at the throat. Even the mass of a single person, about 70 kilograms, introduces a perturbation. And the calculations suggest that this perturbation could initiate a positive feedback loop. The additional mass increases the curvature, which increases the gravitational forces, which further narrows the throat, which increases the energy density, which further increases the curvature. And so on. The throat collapses, and you are caught inside a rapidly shrinking tunnel of curved space-time that is becoming a singularity. You do not travel through to the other side. You are obliterated. The astrophysicist Paul Sutter summarized this with memorable directness when he wrote, and I quote, "Don't ever travel down a wormhole. You'll die." He went on to explain that if you were to find a wormhole and send a single bit of light through it, just a single photon, this alone could be enough to create a cascade effect that would destroy the wormhole. The structure is that fragile, that sensitive, that deadly. The fourth danger is one that might not kill your body, but could break the universe. Causality violation. If wormholes can connect different points in time as well as space, and the mathematics says they can, then they open the door to time travel. And time travel opens the door to paradoxes. The most famous is the grandfather paradox. You travel back in time through a wormhole and prevent your own grandfather from meeting your grandmother. Your parents are never born. You are never born. But if you were never born, you could never have traveled back in time to prevent the meeting. So your grandparents do meet, and you are born, and you do travel back, and we are stuck in an infinite logical loop with no resolution. But the paradoxes are not just philosophical puzzles. They may represent real physical instabilities. If a wormhole configuration approaches the point where it would allow a closed time-like curve, a path through space-time that loops back to its own starting point in both space and time, then quantum effects might become extremely violent in the vicinity of the wormhole. Vacuum fluctuations, those same quantum fluctuations that produce the Casimir effect, could amplify as they loop through the wormhole time machine again and again, each pass adding energy, building up to a crescendo of infinite energy density that would tear the wormhole apart. This is the essence of Stephen Hawking's chronology protection conjecture, proposed in 1992. Hawking suggested that the laws of physics conspire to prevent the creation of closed time-like curves. He argued that whenever a wormhole or any other space-time structure approaches the point where it would enable time travel, quantum effects kick in and destroy it. The universe, in Hawking's view, has a built-in immune system that protects the timeline from paradoxes. He famously said that this makes the universe safe for historians, because it means no one can go back and change the past. But not everyone agrees with Hawking. Matt Visser, one of the world's leading experts on wormhole physics, proposed a counterexample in 1997 called the Roman ring, named after the physicist Tom Roman. The idea is this. Imagine arranging multiple wormholes in a circular network, a polygon. Each individual wormhole in the ring has a small time shift, not enough by itself to create a closed time-like curve, but the cumulative effect of traveling through all the wormholes in sequence could add up to a time loop. Visser showed that Hawking's mechanism, the buildup of vacuum energy, might not apply to this configuration because each individual wormhole is not, on its own, a time machine. To his credit, Visser himself was cautious about the implications, noting that this is more likely a sign that our current theories of quantum gravity are incomplete than it is evidence that time travel is actually possible. And this brings us to one of the most profound and beautiful ideas in all of theoretical physics, an idea that connects wormholes, quantum mechanics, and the very fabric of reality in a way that nobody expected. The year was 2013. Two of the most brilliant theoretical physicists alive, Juan Maldacena of the Institute for Advanced Study and Leonard Susskind of Stanford University, published a paper with a title that looked more like a mathematical equation than a physics proposition. The title was simply ER equals EPR. To understand what this means, you need to know about two separate papers, both published in 1935, both co-authored by Albert Einstein, addressing completely different topics. The first paper, which we have already discussed, was the Einstein-Rosen paper, ER. This paper described the Einstein-Rosen bridge, the wormhole. It was about gravity, geometry, the large-scale structure of space-time. The second paper was the Einstein-Podolsky-Rosen paper, co-authored by Einstein, Boris Podolsky, and Nathan Rosen. EPR. This paper was about quantum mechanics. Specifically, it described a phenomenon called quantum entanglement, which Einstein famously and dismissively called spooky action at a distance. When two particles are entangled, measuring a property of one instantly determines the corresponding property of the other, no matter how far apart they are. Einstein found this deeply troubling, because it seemed to imply that information was traveling faster than light, violating his own theory of relativity. The EPR paper was intended as an argument that quantum mechanics must be incomplete, that there must be hidden variables determining the particle's properties in advance. For 78 years, these two papers were treated as completely separate contributions to two completely separate fields of physics. ER was about gravity and spacetime. EPR was about quantum mechanics and entanglement. Nobody connected them until Maldacena and Susskind. Their conjecture, ER equals EPR, proposes something breathtaking. Every pair of entangled particles is connected by a wormhole. Every Einstein-Rosen bridge is a manifestation of quantum entanglement. Wormholes and entanglement are not separate phenomena. They are the same phenomenon, viewed from different perspectives. ER is the gravitational geometric description of a connection. They are two sides of the same coin. If this is true, and I want to emphasize that ER equals EPR is a conjecture, not a proven theorem, but if it is true, the implications are staggering. It would mean that wormholes are not exotic, rare speculative structures. They are everywhere. Every entangled particle pair in the universe, and there are unfathomably many of them, is connected by a microscopic Einstein-Rosen bridge. The entire fabric of space-time, the very arena in which physics takes place, might be woven together by an incomprehensibly vast network of tiny quantum wormholes. Space-time itself might emerge from entanglement. The geometry of the universe might be a consequence of quantum information. But these quantum wormholes are not like the macroscopic traversable wormholes we have been discussing. They are non-traversable. You cannot send information, matter, or energy through them faster than light. They do not violate the no-communication theorem of quantum mechanics. They are geometric connections, not usable tunnels. They explain why entanglement works, providing a geometric reason for the correlation between measurements on distant particles, without allowing faster-than-light communication. The spooky part of spooky action at a distance is replaced by a concrete geometric connection, but the no-information transfer rule is preserved. The R equals EPR conjecture also has profound implications for one of the biggest unsolved problems in physics, the black hole information paradox. In 1974, Stephen Hawking made one of the most important discoveries in theoretical physics. He showed that black holes are not entirely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly shrink and eventually evaporate completely. But here is the problem. The Hawking radiation is thermal, which means it is essentially random. It does not carry any information about what fell into the black hole. When the black hole finally evaporates away completely, all the information about everything that ever fell into it, every book, every person, every star, seems to be lost. Gone. Erased from the universe. This violates a fundamental principle of quantum mechanics called unitarity, which says that information is never truly lost. Quantum mechanical evolution is reversible. You can always, in principle, reconstruct the past from the present. But if a black hole can destroy information, then quantum mechanics is wrong at a fundamental level. This is the black hole information paradox, and it has been the subject of fierce debate among physicists for over 50 years. ER equals EPR offers a beautiful potential resolution. If the Hawking radiation particles are entangled with the interior of the black hole, and if entanglement equals wormhole connection, then the radiation and the black hole interior are connected by a vast network of ER bridges. Information that falls into the black hole is not lost, it is encoded in the entanglement between the black hole's interior and its Hawking radiation. As the black hole evaporates, the information gradually leaks out through these quantum connections, preserved but scrambled, like a message that has been encrypted but not destroyed. This idea gained dramatic experimental support, or rather, experimental analog support, in November 2022, when a team of researchers from Caltech, Harvard, Fermilab, and Google Quantum AI published a remarkable paper in the journal Nature. Using Google's Sycamore 2 quantum processor, a quantum computer with 72 qubits of which they used 9, the team created a quantum system whose behavior is mathematically equivalent, or dual in the technical language, to a traversable wormhole in a simplified model of quantum gravity. Here is what they did. They prepared a quantum state in one part of the processor and showed that the information in this state was transmitted to a distant part of the processor through a process that, in the mathematical framework of the ADS/CFT correspondence, is described as traversal through a wormhole. The information entered one side of the quantum wormhole, passed through, and emerged on the other side. The dynamics matched the theoretical predictions for how a traversable wormhole would behave. Now, I must be very clear and precise about what this experiment did and did not show. It did not create a real wormhole in physical space-time. No tunnel through space was generated in a laboratory in California. What the experiment showed is that the quantum mechanical description of wormhole traversal can be implemented on a quantum computer, and that the results match theoretical predictions. It is a proof of principle, a demonstration that wormhole-like dynamics are not just mathematical abstractions, but can be realized in a physical quantum system. It is a quantum simulation of a wormhole, not a wormhole itself. The distinction is important, but the result is nonetheless remarkable, because it is the first time anyone has observed wormhole dynamics, even in an analog system. And now I want to bring you to the absolute cutting edge, the research that is happening right now in 2025 and 2026 that is changing our understanding of what wormholes really are. In January 2026, a paper was published in the prestigious journal Classical and Quantum Gravity that proposes a radical reinterpretation of the Einstein-Rosen bridge. The authors, building on recent work by researchers Shravan Kumar and Joao Marto, argue that the Einstein-Rosen bridge is not a tunnel through space at all. It is a mirror in time. Let me explain what this means because it is genuinely mind-bending. Most fundamental laws of physics are symmetric with respect to time. If you take the equations of motion and replace time with negative time, running time backwards, the equations still work. A ball thrown upward and then falling back down looks perfectly physical, whether you run the film forward or backward. This symmetry is called time reversal symmetry, or T-symmetry. The laws of physics do not inherently prefer one direction of time over the other. The arrow of time, our experience that time flows from past to future, is not built into the fundamental equations. It emerges from statistical mechanics and thermodynamics, from the tendency of systems with many particles to move from ordered states to disordered states. The 2026 paper takes this symmetry seriously. If the laws of physics are time reversal symmetric, then a complete quantum description of any physical system should include both time directions. In normal situations, we can get away with ignoring the time-reversed component. We simply choose an arrow of time and work with it. But in extreme environments, near black holes, in the early universe, at the Big Bang, both time directions become important. Both are needed for a consistent quantum description. And the Einstein-Rosen bridge, the authors argue, is precisely the structure that connects these two time directions. It is not a passage from one place to another. It is a passage from one direction of time to the other, a mirror that reflects the arrow of time. In one component, time flows forward. In the other, time flows backward from its mirror-reflected position. The bridge is where these two temporal components meet. If this interpretation is correct, it has stunning consequences. For one, it offers a natural resolution to the black hole information paradox that is different from, but complementary to the ER equals EPR approach. Information that falls into a black hole does not vanish. It continues to evolve, but along the reversed temporal direction. From our perspective, with our forward-flowing arrow of time, it looks like the information is lost. But from the perspective of the complete quantum description, which includes both time directions, the information is preserved. It has crossed the temporal mirror. Completeness and causality are maintained without invoking exotic new physics, without invoking anything beyond what general relativity and quantum mechanics already provide. Even more remarkably, this framework suggests that what we call the Big Bang might not be the absolute beginning of everything. It might be a bounce, a quantum transition between two time-reversed phases of cosmic evolution. Before the Big Bang, the universe was contracting, with time flowing in the opposite direction to ours. At the bounce point, the Einstein-Rosen bridge connects the two phases, and the expanding universe we inhabit emerged on the other side. The Big Bang is not a creation event, it is a temporal mirror, a doorway between two cosmic epochs. And if this is true, there might be relics, physical objects from the pre-bounce phase that survive the transition and persist in our expanding universe. The authors suggest that some of the unseen matter that we attribute to dark matter, that mysterious substance that makes up about 27% of the universe's mass energy, but has never been directly detected, could be made of such relics. Black holes and other compact objects from the previous cosmic epoch, having crossed the temporal bridge, could populate our universe as dark matter. This is speculative, of course, highly speculative, but it is grounded in mathematics, consistent with general relativity and quantum mechanics, and it makes testable predictions. Specifically, the cosmic microwave background, that ancient light from the early universe that fills all of space, shows a small but persistent anomaly. There is a slight asymmetry, a preference for one spatial orientation over its mirror image, that standard cosmological models struggle to explain. The probability of this anomaly occurring by chance in the standard model is extremely low. But if the complete quantum description with both time directions is correct, this asymmetry has a natural explanation. It is a relic signature of the temporal mirror structure. And in April 2026, another significant development. New research has been published suggesting that the energy requirements for wormholes might have been overstated. In certain modified gravity frameworks, particularly those involving higher dimensional structures consistent with string theory, the amount of exotic matter or negative energy needed to sustain a wormhole is significantly less than previous calculations suggested. Some models show that in specific parameter regimes, the energy requirements become physically achievable, at least in principle. The theoretical landscape is shifting. Wormholes are becoming less impossible with each passing year. Not more possible in any absolute sense, we still have no experimental evidence, but the theoretical barriers that once seemed insurmountable are being eroded by careful mathematical work. Now, I want to step back and give you the complete picture. Let us categorize everything we know and do not know about wormholes as of 2026, what we know for certain. Wormholes are valid mathematical solutions to Einstein's field equations of general relativity. The Schwarzschild solution naturally contains an Einstein-Rosen bridge, though it is non-traversable. The Casimir effect demonstrates that negative energy density is physically real, at least in microscopic amounts. The equations of general relativity permit traversable wormholes if exotic matter with negative energy density is present. Certain modified gravity theories allow wormholes without exotic matter. The ER equals EPR conjecture connects wormholes to quantum entanglement at the deepest level. Wormhole-like dynamics have been simulated on a quantum computer. What is theoretically possible but unconfirmed? Traversable macroscopic wormholes sustained by exotic matter or modified gravity effects. Natural primordial wormholes that formed during the Big Bang and were inflated to macroscopic size by cosmic inflation. Wormhole-based time machines, though Hawking's chronology protection conjecture suggests the universe would prevent them. Detection of wormholes through gravitational lensing, gravitational wave echoes, or shadow observations. The reinterpretation of Einstein-Rosen bridges as temporal mirrors connecting two arrows of time. What we do not know: whether macroscopic wormholes exist anywhere in the universe, whether exotic matter can be produced in quantities sufficient to sustain a wormhole, whether the ER equals EPR conjecture is correct, whether the chronology protection conjecture truly prevents all forms of time travel, whether the 2026 temporal mirror interpretation will hold up under further scrutiny, whether GW19, 0521, or any other gravitational wave signal has actually passed through a wormhole, what is almost certainly science fiction, at least for the foreseeable future. Instantaneous portal-style doorways between distant locations, human interstellar travel through engineered wormholes, practical time machines, communication with parallel universes through interuniversal wormholes. So where does this leave us? I want to talk about what I think is the deepest lesson of wormhole physics, and it is not about space travel or time machines. It is about the nature of reality itself. For most of human history, we have thought about space and time as fixed, absolute, unchanging, a stage on which the drama of the universe plays out. Newton's absolute space and absolute time, but Einstein showed us that the stage itself is dynamic. It bends, it stretches, it curves. Mass tells space-time how to curve, and space-time tells mass how to move. And wormholes take this one step further. They show us that the topology of space-time, its fundamental shape and connectedness, might not be what we naively assume. Space might have holes, shortcuts, hidden passages. The geometry of the universe might be far richer and more complex than the simple three-dimensional space we perceive in our everyday lives. And if ER equals EPR is correct, then this complexity goes all the way down to the quantum level. The fabric of space-time is not a smooth, continuous sheet. It is a vast network of quantum connections, an unimaginably complex web of entanglement that gives rise to the geometry we experience. Space is not fundamental. Geometry is not fundamental. Entanglement is fundamental. And wormholes, those theoretical bridges through space-time, might be the threads from which the tapestry of reality is woven. This is a profoundly humbling idea. It suggests that the space around us, the apparently empty void between objects, is not truly empty and not truly separate from other regions of space. Everything is connected, not in some vague, mystical sense, but in a precise mathematical physical sense. The geometry of the universe encodes relationships between distant things, and wormholes are the mathematical expression of those relationships. Even if we never travel through a wormhole, even if we never detect one, even if macroscopic wormholes turn out to be truly impossible, the study of wormholes has already given us some of the deepest insights into the nature of reality that physics has ever produced. The ER equals EPR conjecture, the black hole information paradox resolution, the connection between geometry and entanglement, the temporal mirror interpretation. All of these ideas emerge from taking wormholes seriously and following the mathematics wherever it leads. Let me tell you something about the history of physics that I think is relevant here. When Einstein published general relativity in 1915, one of the first exact solutions to his equations was found by Carl Schwarzschild, and it described what we now call a black hole. But for decades, most physicists, including Einstein himself, believed that black holes were mathematical curiosities with no physical reality. They thought that no real physical process could compress matter densely enough to form one. It took until the 1960s and 1970s for the theoretical work of Roger Penrose, Stephen Hawking and others to show that black hole formation is not just possible but inevitable for sufficiently massive stars. And it took until 2015 for the first direct detection of gravitational waves from a binary black hole merger by LIGO, and until 2019 for the first direct image of a black hole shadow by the Event Horizon Telescope. The trajectory from mathematical curiosity to observed physical object took 100 years for black holes. Wormholes are following a similar trajectory, though they are arguably at an earlier stage. The mathematics has been established for nearly a century. The theoretical frameworks for traversable wormholes have been developed over the past 4 decades. The quantum connections through ER equals EPR have been explored for the past decade. Quantum simulations have been performed. Detection methods have been designed. The theoretical landscape is becoming more favorable, with new models showing wormholes might require less exotic physics than we feared. Is it possible that in another 50 or 100 years, we will detect a wormhole that we will find through gravitational lensing or gravitational wave analysis, or some method we have not yet invented, clear evidence of a structure connecting 2 distant regions of space-time? I do not know. Nobody knows. But I would not bet against it. Physics has a remarkable track record of turning mathematical predictions into observed reality. The Higgs boson was predicted in 1964 and detected in 2012, 48 years later. Gravitational waves were predicted in 1916 and detected in 2015, 99 years later. Wormholes were predicted in 1935. The clock is ticking. Now, let me take you through one more thought experiment before we begin to bring this all together, because I think it illustrates the deadliness and the wonder of wormholes better than anything else we've discussed. Imagine that, far in the future, humanity has become a Type 2 civilization on the Kardashev scale. We have harnessed the full energy output of our star, roughly 10 to the power of 26 watts. We have developed the technology to manipulate spacetime at macroscopic scales. We have found a way to produce and contain exotic matter in bulk, and we have built a traversable wormhole. One mouth is positioned in orbit around Earth, the other is positioned somewhere in the Alpha Centauri system, 4 light-years away. We have somehow transported it there, perhaps by accelerating it to near-light speed over decades or centuries. The wormhole is stabilized by a shell of exotic matter around the throat, carefully tuned to keep the throat open. Engineers monitor its stability constantly, making adjustments in real time to prevent collapse. You are invited to be among the first humans to traverse it. You approach the mouth in Earth orbit. From the outside, it looks like a sphere about 10 meters in diameter, floating in the void. Through it, you can see the stars of Alpha Centauri, distorted and warped by gravitational lensing, but unmistakably real. You are looking at another star system, 4 light-years away, as if through a window. You step inside. Now, if the Morris-Thorne engineering specifications have been met, if the tidal forces are less than 1 g, if the radiation has been shielded, if the throat is stable, then the experience might be surprisingly anticlimactic. You might feel a brief moment of disorientation as you transition from one region of space-time to another. The geometry around you is curved in ways that human senses were not designed to process, and there might be a strange sensation of space-time itself warping and flowing around you. But it would be brief. The throat might be only a few meters long. The passage might take only seconds. And then you would emerge on the other side, 4 light-years from where you started, having traveled faster than light in effective terms, while never exceeding light speed locally. But everything I just described depends on every single element of the engineering being perfect. If the exotic matter fluctuates, if the throat narrows by even a fraction, if a stray cosmic ray introduces an unexpected perturbation, if the tidal forces are slightly larger than calculated, if the radiation shielding fails, if the feedback loop initiates, any of these failures, individually, is lethal, and the margin for error is essentially 0. This is not like building an airplane or a submarine, where engineering tolerances allow for some deviation from perfection. A wormhole is a structure where the geometry of space-time itself must be precisely controlled, and the consequences of failure are not a crash or a leak, but annihilation at the fundamental level. This is what makes wormholes the deadliest shortcut. Not that they cannot work in principle, but that the gap between works perfectly and kills everything inside instantly is razor thin. There is no graceful failure mode. There is no emergency procedure. If the wormhole fails while you are inside it, you do not crash land or drift. You are torn apart by tidal forces, incinerated by blue-shifted radiation, and crushed by the collapsing throat into a singularity, all in a fraction of a second. and there is nothing anyone on either end can do about it. Now, the question I know some of you are asking is, would it be worth it? Even with all these dangers, even with all these risks, even with the razor-thin margin between survival and annihilation, would it be worth it? To connect distant stars? To bridge the cosmos? To break the chains of the speed of light? I think the answer is that we do not even need to answer that question right now, because the value of wormholes, the reason they matter, is not primarily about travel. Not yet. Maybe not ever. The value of wormholes lies in what they teach us about the universe. Every time we push the boundaries of wormhole physics, we learn something new about gravity, about quantum mechanics, about space-time, about the nature of reality. The Morris-Thorne paper taught us about energy conditions and the limits of classical physics. The ER equals EPR conjecture taught us about the connection between geometry and information. The quantum computer simulation taught us about the duality between quantum systems and gravitational physics. The 2026 temporal mirror research is teaching us about the arrow of time and the possibility of a cosmic bounce. Each of these insights is independently valuable, regardless of whether we ever build or find a real wormhole. And that, I think, is the real lesson of this entire journey. The universe's deadliest shortcut is also the universe's deepest teacher. The mathematics of wormholes opens windows not just to other places and other times, but to other ways of understanding reality itself. The bridge that Einstein and Rosen discovered in 1935 was never just a bridge through space. It was a bridge between theories, between general relativity and quantum mechanics, between our current understanding of physics and whatever comes next, between the known and the unknown. Let me now tell you about one more fascinating avenue of thought that brings together almost everything we have discussed. It concerns the possibility that wormholes might exist naturally in the universe, not as engineered structures, but as remnants of the very earliest moments of cosmic history. The idea was first seriously proposed by Matt Visser in 1995 and has been developed by numerous researchers since then. The scenario goes like this. In the extremely early universe, during the first tiny fraction of a second after the Big Bang, conditions were extraordinarily extreme. Temperatures were billions upon billions of degrees. Energy densities were incomprehensibly high. And the universe was undergoing a period of incredibly rapid expansion, called cosmic inflation, during which space expanded faster than the speed of light, doubling in size every tiny fraction of a second. This expansion was driven by a quantum field called the inflaton. And during inflation, the universe expanded by a factor of at least 10 to the power of 26 in an inconceivably brief time. Now, during this epoch, quantum fluctuations, the same random variations in energy that produced the Casimir effect, were amplified by the exponential expansion to macroscopic scales. These fluctuations are what later grew into the large-scale structure of the universe, the galaxies, galaxy clusters, and cosmic web that we observe today. But Visser and others have proposed that, in addition to density fluctuations, the quantum foam at the Planck scale, those tiny wormholes constantly appearing and disappearing in the fabric of space-time might also have been inflated to macroscopic size during this period. If a Planck-scale wormhole happened to form at just the right moment during inflation, and if it was held open by some mechanism, perhaps cosmic strings with negative mass, perhaps quantum effects in the extreme conditions of the early universe, then cosmic inflation could have stretched it from a size of 10 to the negative 35 meters to astronomical scales. If such primordial wormholes exist, they could have survived to the present day. They would be ancient structures, as old as the universe itself, potentially connecting regions of space that are now billions of light years apart. And they would be extraordinarily difficult to detect, precisely because they might look very much like black holes from the outside. The only way to distinguish a primordial wormhole from a black hole would be through the subtle differences in gravitational lensing, shadow properties, or gravitational wave signatures that we discussed earlier. There is even a proposal connecting primordial wormholes to dark matter. If tiny, Planck mass wormholes were produced in great numbers during the early universe, they would behave gravitationally much like very small, very light particles. They would interact gravitationally but not electromagnetically. They would be stable. They would be everywhere. In other words, they would look exactly like dark matter. This is a highly speculative idea, and there are significant challenges and objections, but it illustrates the fertility of wormhole physics. Even the most speculative corners of the field can generate testable hypotheses about real cosmological questions. The 2026 temporal mirror research adds another layer to this picture. If the Big Bang was a bounce, a transition between a contracting phase with a reversed arrow of time and our expanding phase, then the bounce point itself is a kind of Einstein-Rosen bridge, a temporal mirror connecting two cosmic epochs. Black holes from the pre-bounce universe might have survived the transition, passing through the temporal mirror and emerging in our universe as dark matter candidates. In this framework, our entire universe is, in a sense, the other side of a wormhole. We are living inside a bridge. That is a staggering thought. Not that wormholes might exist somewhere out there in the distant cosmos, but that the cosmos itself, the expanding universe we inhabit, might be the interior of a wormhole-like structure connecting two phases of cosmic evolution. The Big Bang is not a wall at the edge of time, it is a door. And, with that mind-expanding possibility in mind, let me bring this entire discussion full circle. We started this journey with a question. What if there were a shortcut through the universe, a way to bypass the vast distances that separate the stars? And we have learned that such shortcuts, wormholes, are not just science fiction fantasies, they are mathematically valid solutions to the equations that govern the behavior of space-time. They were discovered by Einstein and Rosen in 1935, named by Wheeler in 1957, shown to be potentially traversable by Morris-Thorne in 1988, connected to quantum entanglement by Melder-Sainer and Susskind in 2013, simulated on a quantum computer in 2022, and reinterpreted as temporal mirrors in 2026. The story of wormhole physics is a story of 91 years of human ingenuity, creativity, and relentless curiosity about the nature of reality. But we have also learned why they are the deadliest shortcut: tidal forces that spaghettify, radiation that incinerates, instabilities that collapse, paradoxes that might shatter causality itself, and the universe's own immune system, the chronology protection conjecture, that might destroy any wormhole that threatens the flow of time. We have learned about exotic matter, the mysterious substance with negative energy density that might be needed to hold a wormhole open. We have seen that the Casimir effect proves negative energy is real, even if the amounts are far too small for practical use. We have explored the tantalizing possibility that modified gravity theories might allow wormholes without exotic matter at all, and that the brand world models from string theory could make traversable wormholes more achievable than we ever expected. We have traveled from Einstein's reluctant discovery to Carl Sagan's imaginative phone call, to Kip Thorne's rigorous engineering specifications, to Google's quantum computer laboratory, to the LIGO gravitational wave observatory, to the cutting edge of 2026 cosmological research. We have explored the mathematical, the physical, the philosophical, and the existential dimensions of wormholes. And what I hope you take away from all of this is not just a collection of facts about a theoretical structure in physics. What I hope you take away is a sense of wonder. Because here is what strikes me most deeply about the entire subject. We are small creatures on a small planet orbiting an ordinary star in an ordinary galaxy. We live for maybe 80 or 90 years. We can see, with our unaided eyes, only a tiny fraction of the electromagnetic spectrum. We can hear only a narrow range of sound frequencies. Our brains evolved to track fruit and predators on the African savanna, not to contemplate the curvature of space-time in 11 dimensions. And yet we have managed, through the sheer power of our minds, working with mathematics and logic and imagination, to discover that the universe might contain tunnels, shortcuts, bridges, hidden connections that link distant galaxies, parallel universes, different eras of cosmic history, and the two arrows of time itself. We have managed to write down the equations that describe these structures. We have managed to calculate their properties, assess their stability, estimate their energy requirements, and design methods to detect them. We have even managed to simulate their dynamics on a quantum computer. Is that not extraordinary? Is that not the most remarkable thing about the human species? Not that we might someday travel through a wormhole, but that we have managed to conceive of them, describe them, and begin to test them. All from our tiny perch on this little blue dot. The universe is vast beyond comprehension. The distances are imprisoning. The speed of light is a hard limit that no amount of engineering seems likely to overcome through conventional means. But the mathematics hints at shortcuts. The equations whisper about bridges. And as long as those whispers persist, as long as the equations allow for the possibility, we will keep exploring, keep calculating, keep pushing the boundaries of what we know and what we might someday be able to do. Wormholes may be the universe's deadliest shortcut, but they are also the universe's most tantalizing invitation. An invitation to go further, to think deeper, to explore more boldly than we ever have before. An invitation whispered in the language of mathematics, hidden in the curvature of spacetime, and addressed to anyone curious enough to listen. Now, let me give you one final piece to think about as we wrap up this incredible journey together. Remember the 2026 research about the temporal mirror interpretation? The idea that Einstein-Rosen bridges connect two arrows of time, that the Big Bang might be a bounce rather than a beginning, that our universe might have had a history before what we call the start of time. If that interpretation holds up, if future observations and calculations confirm it, then it will not just change our understanding of wormholes, it will change our understanding of everything. Because think about what it means. If the Big Bang was not the beginning, if there was a before, if time extends in both directions from that cosmic mirror point, then our universe is not a singular event. It is one of at least two phases of cosmic evolution. And the Einstein-Rosen bridge that connects them is not a theoretical curiosity tucked away in the exotic corners of physics. It is the most important structure in the history of the cosmos. It is the hinge on which reality swings. The point where contraction became expansion, where the past of one epoch became the future of another, where everything changed. And the evidence might already be there, hiding in plain sight. That anomaly in the cosmic microwave background, the persistent asymmetry that has puzzled cosmologists for 20 years, the signal that standard models assign an extremely low probability, might be the fingerprint of the temporal mirror, a faint echo of the bridge that gave birth to our universe. If further analysis confirms this, we would have something unprecedented, observational evidence, from the oldest light in the universe, for a structure that Einstein and Rosen first described mathematically in 1935, 91 years from prediction to potential detection. Another triumph of theoretical physics, another vindication of the power of mathematical reasoning to reveal the hidden architecture of reality. But I also want to leave you with a healthy dose of scientific humility. Theoretical physics is full of beautiful, elegant, mathematically consistent ideas that turned out to be wrong, or incomplete, or applicable only in regimes that do not actually exist in our universe. The temporal mirror interpretation might not survive further scrutiny. The ER equals EPR conjecture might turn out to be an approximation rather than an exact truth. The wormhole interpretation of GW190521 might be ruled out by future data, and exotic matter, in the quantities needed for macroscopic wormholes, might be genuinely fundamentally impossible. That is the nature of science. We follow the evidence, we follow the mathematics, we make predictions and test them, and we accept the results, even when they disappoint us. The beauty of wormhole physics is not that it promises us shortcuts through the cosmos. It is that it stretches our minds, expands our concepts, and pushes us toward a deeper understanding of reality, whether or not that understanding includes traversable tunnels through space-time. So the next time you look up at the night sky and see those distant stars, those faint points of light so impossibly far away, remember this. The equations that describe the space between you and those stars also allow for connections, bridges, shortcuts through the fabric of reality itself. They might be deadly. They might be impossible. They might be far more strange and wonderful than anything we have yet imagined. But they are there, in the mathematics, waiting for us to understand them. The universe's deadliest shortcut is still out there, somewhere in the curvature of space-time, challenging us to be bold enough, clever enough, and careful enough to find it. And maybe, just maybe, to survive it. Thank you for staying with me through this entire journey. If this exploration of wormholes has expanded your mind, if it has given you a new appreciation for the depth and beauty and strangeness of the universe we live in, if it has sparked even a single new question in your curious mind, then I am deeply grateful for your time and attention. If you want more deep dives into the most fascinating and mind-bending topics in space science, you know what to do. Like this video, subscribe to the channel, drop a comment telling me where you would go if you found a wormhole. Would you travel to a distant galaxy? Would you visit the past? Would you step into another universe? Or would you look into the temporal mirror and try to glimpse what came before the Big Bang? I want to hear your thoughts. Until next time, keep looking up, keep asking questions, and never stop being curious about this beautiful, mysterious, terrifying, and wondrous universe we call home. End.